students, in the today lesson, we will study about the diagonalization of a matrices which is called orthogonal diagonalization, and furthermore the we will see the orthogonal matrices, and we also see the one of the most important theorem which is called the spectral diagonalization, from the things that how we can make the spectral diagonalization. And we will also then see about the some problems where the results, how to obtain the spectral decomposition of a some given matrix. So let's start for that one. So the topic will be start with one of the nice metric, square metric, mean n cross n matrix is called orthogonal metric if its transpose is same as its inverse. Means if you take the transpose of a metric, then A transpose is equal to A inverse. And we know that if a metric have its inverse, then if you multiply either on its left side or right side, both case it will becomes identity. So the orthogonal metric always satisfies this condition that A times A transpose is equal to A transpose A, and that is equal to the identity metric. So the orthogonal metric have some important applications and some useful examples. For instance, one can see the is the given square metric is the 3 cross 3 square metric is the orthogonal or not. So what we need to do is that we just take its transpose. Transpose mean row will interchange into the columns and columns will change into the rows, and we need to multiply in the left side as well as on the right side. And when we multiply, we know that first row with first column, first row with second column gives us second entry. Similarly, the first row with third column gives us third entry. Second row, first column gives us this entry, the first row, second row, first column. Similarly, the second row multiply with the column, second row multiply with third column. So this is the standard rule for the product. I hope you know in your elementary courses. So it will when you multiply them, we will get identity metric. So it means the A transpose behaves same as the A inverse, and hence it means that A is a diagonal metric. A is the orthogonal metric. So orthogonal means that its a diagonal entry product will gives you the its norm, which is default norm is 1, and it also means that the rows and columns, the rows is a vector and columns are also the vectors. If you multiply them with the distinct of them, you will obtain the zero. Zero means it will gives you the when the product of two vector is zero, it means both vectors are orthogonal to each other, mean perpendicular to each other, or their product is equal to the zero. So that's why we call it orthogonal metric. Now, here we can see some other example, like if you take A is equal to cos theta minus sine theta cos theta. So this is the standard metric with some angle theta. Sometimes we call it counterclockwise rotation matrix of R2. Now, if you take A transpose and multiply with A, then we know that it will becomes cos square plus sine square, and cos square plus sine square is 1. And similarly here, if we multiply the rest of entries, so other entries will become 0. And moreover, minus sine square times minus sine square is plus sine square and plus cos square. So sine square plus cos square is again will becomes 1. So mean whatever the values of theta, so this metric A is always the orthogonal metric. And again, you can notice that so the rows multiplied by columns will gives you the 1, 0, and 0, 1 for this case. So it have some we can see another useful result from that one, like the followings are equivalent for n cross n metric. So remember that the metric A must be a square metric. Now, if A is a orthogonal metric, then the row vectors, look here, that the row vectors of an orthogonal matrix set in Rn with Euclidean inner product. Euclidean means the inner product which we are using in Rn. The row vectors of A form an orthonormal. Orthonormal means like when you multiply the rows of that one, you will get the one. on that entries. And similarly, the column vectors of A form an orthogonal set in Rn. So under the usual or under the Euclidean inner product. And we can see the thing over here that whenever you A multiply with A transpose, so it will behave that R1 multiply with R1. Similarly, R2 multiply with R2 on the diagonal entries, and the rest of entries R1 multiply with R2, R2. So like in that entries, you can see it will be, gives you the product which is equal to 0. It means the rest of entries all are 0, like R1 multiply R2 is 0, R1 multiply R3 up to R1 multiply by Rn. So all upper entries are 0, all lower entries are 0, and R1 times R1 is 1, which means it's not only the orthogonal, but it's also the orthonormal. Normal mean inner product is equal to the 1. So since the self inner product is 1, so that's why we call it orthonormal. So either you take it's the row forms are in column forms, because the important thing is that if A is orthonormal, then A transpose is also orthonormal. So that's why either you take its rows form or a column form. In the both case, it performs as a orthonormal set of Rn. So it means the all of rows R1, R2 up to Rn is orthonormal set in Rn. Now, this is the interesting results that if A is orthogonal metric, then inverse is its inverse is also orthogonal, and the product of two orthogonal metrics is orthogonal. This is a useful result, and we can get its results with simple calculations. And moreover, uh, if A is orthogonal, then the determinant of A is either 1 or determinant of A is equal to the minus 1. So this has also some useful applications of that one. And remember that the transpose of orthogonal metric is also orthogonal, and inverse of orthogonal metric, because inverse is equal to A transpose, and hence its mean A transpose is also orthogonal. And one can see some examples regarding that, like if you have this metric and if you find its determinant, so determinant is either will becomes 1 or minus 1. So this will be always true for orthogonal matrix. So here this is also the another equivalent result, that if A is orthogonal, then if you multiply A times x, then take its norm or length, then it is same as the norm of x. And moreover, AX inner product with AY under the Euclidean inner product is same as x times y. And its proof is available over here with the short calculations. You can see that they use the inner product with matrix, and hence it's conclude because A transpose A is equal to identity. So identity times multiply with any vector is will becomes the same vector. So this is the, since it's a Euclidean product or Euclidean mean product of Rn, like just multiply the vectors with each others, so it will becomes the norm. And hence norm of Ax is equal to the norm of x. Similarly, the proofs of others are available over here. Now, this is also true that if you take its component like under the inner product, if S is orthogonal basis of Rn with the inner product space V, and if Vs is taking the coordinates like u1, u2 up to un, and Vs is the v1, v2 up to vn, then the norm of u will be same as its distance from the origin, and distance between u and v, we can see that these are always true. So these are some results about the orthonormal, the orthogonal matrices. Now further we will come to see the next topic, which is the orthogonal diagonalization. So this is an interesting and important diagonalization before we see the diagonalization of a matrix. But here, what happened if you have a square matrix A which is orthogonal? And here we can see some of its useful results. So the first definition is, if A and B are square matrix, then we say that A and B are orthogonally similar to each other if there is a orthogonal metric P such that P transpose AP is equal to the B. Now here you have to be noticed that in simple diagonalization we need to take a metric P where P instead of P transpose we take P inverse, like P inverse AP is equal to the D. But here in this case it will becomes little change, because if instead of its inverse, we use the transpose of P. And it means that if A is orthogonally similar to some diagonal metric D, then the definition will becomes P transpose AP is equal to the D. And here D will always contain the diagonal entries. And from the previous lessons, you have noticed that in the diagonal matrix, the diagonal entries are eigenvalues. And in the P, it contains the eigenvectors in the same order as we are using the order of a eigenvalues in the diagonal entry. So same order we will also adjust the vectors. But here there is one thing useful, like when we say about the P, instead of P transpose P inverse, we use the P transpose. And it will be always orthogonally diagonalizable because it have some reasons which we will see now, that how what is the reason why we call it orthogonally diagonalized. The important thing is that all of its vectors, like eigenvectors, all eigenvectors are orthonormal each other. When you multiply the vectors of P with each other, like you multiply the rows or multiply with the columns with each other, so you will get their inner product is equal to the zero. And when you will take the self inner product of the, like R1 multiplied by R1, you will get the 1. So that is the important reasons. But let's see that how we can apply this method. And one thing more is that if a metric is orthogonally diagonalizable, then it means such a metric will always be similar. Here one can see that if you apply the transpose on that, so it will becomes the whole transpose, and it will interchange the entries. The transpose of a transpose is always equal to the same metric. And since D is a diagonal metric, so transpose of diagonal metric is again D, because it doesn't affect anything. And again we will get the A. It means if A is orthogonally diagonalizable, then A will always be symmetric, and hence this result is also equivalent. Means if A is symmetric metric, then it means such a metric is orthogonally diagonalizable metric. Now, so this is also the useful result, that if A is orthogonally diagonalizable, then A has orthonormal sets of n eigenvectors. Mean orthonormal means all of its vectors are orthonormal. Mean their self inner product is 1, and their inner product with each other is equal to 0. And it contains the n distinct eigen vectors. And moreover, all the eigenvalue, the metric A is also symmetric. Here we can see one of its result. Like here, there are some basic proofs. We will comes towards the example, but let us see some other results regarding that. Like if A is symmetric metric, then the eigenvalues of A are always real numbers. Like every symmetric metric has the eigenvalues, they will be always real, they will never be complex. And moreover, the eigenvalues from different eigenspaces are orthogonal. Like this is also the beautiful result regarding the symmetric metric. Like if the metric is symmetric, then its eigenvalues, eigenvectors are always orthogonal. Mean if you multiply their eigenvectors, so you will get their inner product will be 0 with the distincts of that one. So and we know that we have a Gram-Schmidt process which we can use and make it normalize. Here we can see some results regarding that is, so how to find the orthogonally diagonalization of a some given metric. The first thing is that need to find its eigenvalues and eigenvectors of a given metric. So when you will find the eigenvalues and eigenvectors, then we know the Gram-Schmidt process, which always gives us a orthonormal basis of that given spaces. So given basis set. So we need to apply the Gram-Schmidt process and make them orthonormal, not only the orthogonal, make them orthonormal. And then from that orthonormal basis, if we combine, we can generate a metric P. So that metric P has a beauty that if you take its transpose and then multiply with A and P, then it will always equal to a metric D. Such a metric D is a diagonal metric, and its diagonal entries always contained the eigenvalues of a given metric A. So that is the important relation between that. And one can see some, let's see one example regarding this. For instance, if we need to find the orthogonally metric P such that this metric is orthogonally diagonalizable, what we need to do is, first of all, we need to find its eigenvalues and eigenvectors. We know that if we can take a characteristic equation like determinant of lambda I minus a is equal to 0, then for solving this, we can get sum of roots of from this equation. So now these roots are always, you know that these roots are always gives us a eigenvalues. So it means it has basically the two eigenvalues. It should be three, but here in this case, look, the lambda is equal to 2 is repeated. So it means the eigenvalues are 2 and 8. So now if you find its eigenvalue, from these eigenvalues, if you find the eigenvectors, then by applying the previous method, how to find the eigenvector, we need to calculate eigenvector. So let's see that we can for from lambda is equal to 2, if we find eigenvector, we get u1 and u2. So these two are the eigenvectors we are obtaining from this. And you have noticed that what happened when we multiply u1 with u2. So if we multiply u1 with u2, so we will get some, we can see that u1 and u2 are not orthogonal to each other. Why? Because if you multiply, so it will becomes minus 1 plus 0 plus, sorry, minus 1 multiplied by minus 1 is 1, plus 1 times 0 is 0, plus 0 times 1 is 1. So it means 0 times 1 is 0. So it means it will becomes 1 plus 0, which is equal to 1. It means u1 and u2 are not orthonormal or orthogonal. So what we need to use it, we need to apply a Gram-Schmidt process to make orthonormal of these two vectors. For instance, if we take u1 is equal to the v1 and then apply to find the u2. And you know that Gram-Schmidt process will also gives us not only the orthogonal but also the orthonormal. Ortho mean perpendicular, like their inner product will be 0 with the other vectors, and moreover, the norm of each vector must be equal to 1. So here, when you take its norm, the norm is equal to the square root 2. So need to multiply with that. So we will get, by using Gram-Schmidt process, we will get v1 and v2. So now you have to be noticed that if we multiply v1 with v2, the answer is 0. Mean both are orthogonal to each other. Both are perpendicular to each other. Their inner product is 0. And moreover, if you take norm of v1, that is equal to 1. The norm of v2 is also equal to 1. And when for the other eigen value, which is 8, we when we find eigenspace or eigenvector for lambda is equal to 8, we will get 1, 1, 1. Now the interesting thing is that if you multiply u1 with u3, it will be perpendicular. Like the inner product of u1 with u3 is 0. The inner product of u2 with u3 is also 0. You can check it. But when they will comes from the same eigenvalue, so they will not perpendicular, then we need to apply the Gram-Schmidt process to make them orthonormalize. Here u3 is orthogonal to the u1 and u2, but it's not orthonormal. How to make them normal? We can use the Gram-Schmidt process, which tell us that if you multiply the norm with if you multiply with 1 over norm of the u3, we will get this value. Like it will be, the norm of u3 is 1 square plus 1 square plus 1 square whole square root, which is equal to the square root 3. So it means u3 is the, v3 is equal to u3 divided by norm of u3. So it will becomes 1 by square root 3, 1 by square root 3, and 1 by square root 3. So here now v1, v2, v3, these are orthonormal. Like v1, if you multiply v1 with v2, then the product is 0. v1 multiply with v3, the product is 0. Moreover, v2 multiply with v3, the product is also 0. And norm of v1 is 1, norm of v2 is 1, norm of v3 is also 1. Now, with the help of that, if we combine, like if we take P as a V1, V2, and V3, we will get a metric P. Now, this metric P has a one beautiful thing, that if you take the transpose of P, multiply with the A, and then multiply with the original P, what you will get? You will get a diagonal metric. And that diagonal metric always contained the eigen values like 2, 2, and 8. So these are the eigen values of a metric. And moreover, if you can see that in the metric, if you multiply the like in a P, if you multiply any of them with each others, so you always get their product will be equal to the 0. So the, because it contains always the it always contains the it what you call it, it's like all of its columns are orthogonal to each other. Not only the orthogonal but orthonormal. The norm of the first, if you will take, it's also equal to the 1. The norm of second column is also equal to 1. The norm of third column is as well 1. And moreover, if you multiply the first column with second, then answer is 0. First column multiply with the second column, the answer is 0. Like it's a vector product, which is called the inner product. And the norm of second column with third column, that is also equal to the 0. One can check it. And this is called the orthogonal diagonalization of a given metric A. So we have noticed that if A is a symmetric metric, then we can obtain a metric P which have orthogonally diagonalized by P is equal to this one. And we can express this thing as A is equal to PD P, and look that if you multiply their entries over there, then A will becomes into the form of a with this formula, like A is equal to lambda 1 u1 multiplied by u transpose plus lambda 2 u2 multiplied by u2 transpose up to lambda n un times un transpose. Now use a vector. If you multiply with its transpose, the column vector with the row vector, it will gives you a metric, a square metric with the same size as A. Like A, if A is a n cross n metric, then U1 time U1 transpose is also a n cross n metric. U2 cross U2 transpose is also the n cross n metric. So up to UN times UN transpose is also gives a n cross n metric. So this is called the spectral decomposition. And this is also the one of the beautiful thing that look, lambda 1, lambda 2, lambda n, these are the eigenvalues. And u1 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 transpose, so these are the its eigenvectors, which are orthogonal eigenvectors. Now which one can see that with the this decomposition, we can express A as a linear combinations of this matrix form, and we call it a spectral decomposition of a given metric A. And this is also the useful thing that let's see how it will work. For instance, if we have a metric A, then if we find the its eigenvalues and eigenvectors, so lambda 1 is the first eigenvalue, which is -3. The second eigenvalue is 2. One can check that sum of eigenvalues is always equal to the sum of diagonal entries. That like 1 plus -2 is -1. And if you make lambda 1 plus lambda 2, means minus 3 plus 2, which is also equal to minus 1. It means the eigenvalues are correct. Now, if you find its eigen corresponding eigenvectors, mean for lambda is equal to minus 3, the eigenvector is this. And for lambda is equal to 2, the eigenvector is this. Note that if you multiply x1 with x2, the x1 times x2 is equal to 0 because lambda 1 is always orthogonal to lambda 2 because A is a symmetric metric. Now, this is orthogonal but not orthonormal. Orthonormal mean the norm should be equal to 1. Lambda 1 norm should be 1, lambda 2 norm should be 1. What we need to use it, we take we need to find u1, which is the norm, which is the x1 divided by norm of x1. So norm of x, you know that it's 1 square plus minus 2 square and whole square root, which is equal to the square root of 5. So if we divide square root of 5 with each of its entry, it will gives us a u1. Similarly, for u2, we can divide the square root 5, means the norm of x2 with each of its entry, so we will get u2. Now note that u1 and u2 are orthonormal. Normal means take the norm of u1, the answer is 1. The norm of u2 is also equal to 1. And if you multiply with u1 and u2, so the answer is 0 because the product of these two vectors is 0. Now one can see the spectral decomposition. Like if you multiply lambda 1 u1 with u1 transpose and plus lambda 2 u2 with u2 transpose. If you multiply them, you will see that these are the eigenvalues. Minus 3 and 2 will come here. So, and if you multiply them, you will get some square metric. So here these are the metric we obtain over here. And so this is the spectral decomposition of a given metric. Like we express a given metric A into the form of its decomposition, where we obtain the two distinct matrices. And the important thing is that here from that we obtain these two matrices, and one can see that how this behave. If you have some vector, like if you multiply, this is your A and this is the its decomposition. Now if we multiply, suppose that we have a one vector 1 1. So if we multiply 1 1 on A, so A times like A is 1 2 2 minus 1 and X is say 1 1. If you multiply them, the answer will be 3 0. On the other hand, if you multiply again this vector 1 1 with the with its right hand side is where this is the right hand side. So if you multiply this number on the other side, so it will multiply with the first element plus second element. It's just a distribution of the multiplication. So if matrix multiply by vector is a vector and matrix multiply by vector is a vector. And now if you multiply with minus 3 the first vector and second vector multiply with the 2, after adding this you will get again 3 0. It means ax equal to 3 0 over here and ax is equal to 3 0 over here. Either you multiply such a x or such a vector with any side of the either with a or multiply with its decomposition, the answer will always becomes the same. So it means from this formula, this always work and give us this kind of a decomposition. And here there are also some other theorems regarding that is like if A is a n cross n metric with real entries and real eigen values, then there exists an orthogonal metric P such that P transpose AP is a upper triangular matrix of the form. So this form we can generate where lambda 1 up to lambda 2, these are the eigenvalues of a metric repeated according to the multiplicity. Like if you multiply them with of metric A repeated according to its multiplicity. And also this is the Hessenberg theorem, which is also states the same that we can obtain this type of a form when we take P transpose AP. So we will again get some this kind of the form of a matrix. So these are the results about that one. Now if we see some other notes regarding that one, mean orthogonal matrix or orthogonal diagonalization. In orthogonal diagonalization, recall that A is a n cross n metric, uh, and which is if for a metric, if we take its transpose, multiply with A and P, then we will get some orthogonal diagonalization of a metric. Like for this case, P is invertible and P inverse plays the same role as a P transpose. Like P inverse is same as a P transpose. It means the row of P are orthogonal and columns of P are also the orthogonal. And here we can see that for a n cross, if A is n cross n metric P, n cross n metric P is called orthogonal metric if it satisfied one of the following condition of the above theorem. So, one can see that we saw before, this is the orthogonal metric, because cos square plus sin square is equal to 1 for any value of a angle theta. And here one can see that we have a metric. This is the given metric has orthogonal rows, but columns are not orthogonal. Like if you multiply the rows to each other, you will get the answer is equal to the product is equal to the product is equal to the zero because they are orthogonal. And now one can normalize them. Normalize means just take the norm of each row and divide with their entries. Like the norm of first is square root 6. So just divide square root 6. The norm of the second one is second row is square root 3. So we need to divide with square root 3. And similarly, the norm of third row is square root 2. So we can divide with that one. So in this way, we can get the orthonormal rows. And so here there are some results like if P and Q are orthogonal matrix, then PQ is also orthogonal. That is P inverse plays same role as a P transpose. So here we can see the some of the examples like the P inverse is also orthogonal, and so some small proofs are available here. Now for n cross n metric, A is orthogonally diagonalizable when we have a orthogonal metric P, for which we can see that P inverse AP is equal to the D, like P inverse plays the same role as a P transpose. We already saw this kind of result over here, and these are some just repetitions of these results with some examples for which you can see that. For instance, here this is the one nice and distinct example. Find orthogonal metric P such that this metric is orthogonal. So for a given metric E, metric A need to find its eigenvalues and eigenvectors. From characteristic polynomial, we can get eigenvalues like lambda is equal to 0, 1, and 6. Now, the corresponding eigenvectors we need to find, as we know that how to find the eigenvectors. So if you find the eigenvectors, you can get x1, x2, and x3. And note that since all the eigenvalues are distinct, so eigenvectors are also distinct. And moreover, these eigenvectors are orthogonal to each other because A is a symmetric metric. If A is a symmetric metric, then uh, your and if the eigenvalues are distinct, then eigenvectors will always be orthogonal. Like if you multiply x1 with x2, you will get the answer 0. x2 multiplied by x3 is 0. x1 multiplied by x3 is also 0. You can check it. Now, if this is so, they are already orthogonal, but we need orthonormal. For P, we always need, for a metric P, we always need orthonormal. Normal mean the norm should, the self norm of each of should be 1. So what we need to do is just take the norm of that, and if you calculate the norm square, then with the P, just divide the norm with each of its entry. Then after writing them into the column forms, we will get a metric P. So this is a metric P. Now this metric P, if you take its transpose, you will always get P inverse. And moreover, if you multiply P transpose AP, then we will get a diagonal metric which always obtained the diagonal entries will always be its eigenvalues. Like 0 is the eigenvalue, first eigenvalue, 1 is the second eigenvalue, and 6 is the third eigenvalue. One can check that if you interchange the order here, like if you put x3 in the first place and x1 in the third place, then it will becomes what? 6 will becomes over here, it will be 6, and here it will become 0 automatically. Like after the product you can check it that it will also interchange the element in the same order. Now here that this is also the theorem that if A is a n cross n symmetric matrix, then one can see that AXY inner product is same as XAY for all columns X and Y. And moreover, if A is metric, then eigenvectors of A corresponding to the distinct eigenvalues are orthogonal. So it means if all the eigenvalues are distinct, then the all of its eigenvalues like if the eigenvalues are distinct, then eigenvectors will always be orthogonal to each other. All the eigenvectors will be orthogonal. And so orthogonals mean they are perpendicular to each other. And these examples, when look, we norm if you will see the above example, we do not need to apply the Gram-Schmidt process because all the eigenvalues are distinct. But what happened when the eigenvalues are not distinct? Like in the previous example, in the textbook we saw, and here in this example, you have noticed that if we find the eigenvalues, so we will get lambda is equal to 0 and lambda is equal to 9. For the 9, the multiplicity is 2. But for the 0, multiplicity is 1, means 0 is coming 1 times, 9 is coming the 2 times. And the eigenvalues or eigenspace for lambda is equal to 0, we will get the first one. And for lambda is equal to 9, we will get the eigenspace, this one. You can check that the this x1 is orthogonal to the x2 and x3, but x2 and x3 are not orthogonal to each other. So what we need to do is we apply the Gram-Schmidt process over here. Just take this as a u1, this is u2, apply the Gram-Schmidt process to make them orthonormal. After making them orthonormal, orthonormal, also make them normal, like just divide the norm with that one. And when you combine, you will get the a metric P where all these things will be orthonormal. And this P has a thing that if you take its transpose, then multiply with A and P, then we will again get a diagonal metric which always contained its diagonal entries. So these are the results regarding that one. And if we see some examples or some problems from the assignment. So here in the first problem, if A is a orthogonal metric, then A inverse is also orthogonal metric. You can see it's the proof will be very simple, and with some steps like we need to show that the A inverse is also orthogonal, like orthogonal metric. And if A and B are orthogonal matrices, then the product of two orthogonal matrices is orthogonal. So here, with the simple steps which are available, you can use it and get the result. In the problem number 2, what is the condition on A and B for which the given metric is orthogonal? We know that if the metric is orthogonal, then then the transpose of a metric is equal to its inverse. So you just need to use that property, like A inverse is equal to A transpose. So the transpose of the given matrix is available. When we use it, like just multiply A times A transpose is equal to identity matrix. If you will take that, then you will get some equations, like first will becomes the it will come the first product will gives you the 1, second product will gives you the 0, because on the right hand side you have identity metric. By comparing their entries, the first entry will be equal to first, second entry will become second, third will becomes third, and the fourth will becomes the fourth. But remember that in the diagonal entries you have a 1 on the right hand side, and the non-diagonal entries you have a 0 on the other side. If you solve them, you can find the values of A and B. Now in the next problem, find a metric P that orthogonally diagonalize. So you have a given metric. So just apply the need to find the eigenvalues and eigenvectors. If the eigenvalues are distinct, then just need to normalize them, their eigenvalues. But if the eigenvalues are not distinct, then for those whose eigenvalues are repeated or multiplicity 2, need to apply the Gram-Schmidt process, and then when you get the orthonormal basis, make them a metric P with their columns, and hence we will get a metric P, and that metric P will gives you that the P transpose AP is equal to the D, where always obtain the diagonal entries. So the diagonal entries will always contain the eigenvalues. You can whatever interchange the order, it always satisfies the relation that P transpose AP is equal to the D, the metric D. And this is another find the spectral decomposition of a metric. We know that the spectral decomposition is actually the A is equal to lambda 1, U1, U transpose plus lambda 2, U2 plus U transpose plus lambda 3, U3, and U times U3 transpose. So, which is already available over here. And remember that for this you need to be verified that, and just need to write this kind of its expressions where u1 u2 and u3s are the orthonormal eigenvectors of the metric. So this is the topic. If you have any question, you can ask your question. Yes, please.
So, sir, for problem 29, do we create matrices of ourselves and use them, or what?
Problem number 29.
Yeah. Do we create our own matrices?
No, no. Look, this is also I have noticed that in the marking that look, when you will show that, it means you need to prove that. But you don't make example. Example will not gives you the proof, because proof will always be general. When you need to prove it or show that, it means A is any metric. Maybe it's a 2 cross 2, 3 cross 3. So you cannot take example like this is the example. So you need to prove it in general by applying the definition. Understand? So here,
Where is the definition, sir?
look, let me show you. For example, here, let me show you some of the proofs. For instance, uh, look, uh, these are equivalent, and like A is these are the result, and here the proof is available, but there is no entries they are using over here. Similarly, you have some proofs available over here. For instance, in the notes, if you will go through, let me. Um, Yes. Look, if P and Q are any matrices, these are orthogonal metric, then the product is also orthogonal. So here this is the proof. Like in that proof, you can see that there is no the example. Like the example will always be hold when the thing will be general proof. So the result will always be true. And do not make any example. If you show with example, then it will be weak. It will be like maybe for that example it will work, but it will not be in general. And remember, when we need to give example, when we disprove, if we want to show that this result is not hold, then we need to show some counter example. For counter example, we need to adopt some take some metric and show that for that metric the result doesn't hold. So when we need to show that its inverse is not true or show that the result is not true, then we need to apply the counter example. Means some example we need to apply and show that. For instance, someone asks you that there is a one set, show that or check that whether it's not a vector space. So suppose if it's not a vector space, then what you need to do is you need to make one example and that show for that vectors it doesn't satisfy the condition of a vector space. So it means that if you want to disprove something, disprove or need to that it doesn't qualify, you need to pick an example for which the result doesn't hold. But if you want to show that something is a vector space, then you need to be prove it in general. Like in general, it satisfies all the conditions. So conclusion is that for example for the problem number 29, you need to prove it in general, not to show the proof as an example. Okay, for instance, like here, you can see that there are some proofs also mentioned over here, or some results. They are all the results will always mentioned in the general form. Any other question? So basically, this topic is about the applications of a orthogonal diagonalization, like orthogonality, the Gram-Schmidt process, and moreover the eigenvalues and eigenvectors, which shows that how they will work. And there are also some other applications of that one. For instance, it can be solved the linear systems when we write it's this kind of diagonalization. So in a later on, you will see that this is also useful to solve the linear systems. Okay, if there is no question, then we should stop over here and best wishes for you. Okay, goodbye.